Hi everyone. It's good to see you, although I guess I can't see you, you can see me. I'm going to take some time here to go through the concepts that you learned last week through the readings in more of a lecture style. So I'm going to set up a little bit of notes that you can look down on as I'm talking, and hopefully that'll review all the concepts.
All right, so what we are learning about in this unit is called uniform circular motion. Now, we've encountered this word uniform before. We talked about just like uniform motion when we were starting our kinematics unit. And what you might remember, what the term uniform means in terms of physics is that things are moving at a constant speed. Now, one thing that you might have noticed in terms of this circular motion from last week is that just because it's moving at constant speed doesn't necessarily mean that it's not accelerating in the case of circular motion, because circular motion implies that something is turning. So one of the key concepts that is connected to uniform circular motion is that there is an acceleration even though the speed isn't changing. So one of the concepts that came up last week is that when we have this circular motion, let's just say we have a ball that is rolling in a circle. Now, in order for that ball to actually be rolling in the circle, it needs to have some force acting on it pointing towards the center of the turn in order to change the direction that it's moving. You might remember when we did our bowling ball races at the beginning of the forces unit, we had to move the bowling ball in a circle. And in order to do that, you had to kind of place the broom on the outside of the bowling ball in order to exert this inward force. In this case, let's just call it a normal force, because in the case of the broom, it would be pushing on the outside of the surface of the ball perpendicular towards the center. Now, one of the reasons that the object actually moves in a circle here is because it already has some speed. It already has a velocity that's moving the ball kind of just tangent to the circle. And then as the ball moves along that circle, you have to continually change the angle with which the broom was kind of contacting that ball in order to continuously change the direction that the ball is moving. But at every point here, the velocity of the ball is actually moving tangent to the circle. And so the speed of the ball doesn't change. We can see that this arrow that represents the vector for the velocity is the same length at every point here. But what is changing is that the velocity here is pointing kind of towards the southeast of this circle, southwest, and here it's pointing more directly south. So the direction is changing. And really, if the direction is changing, then we have to have an acceleration. And from our forces unit, we realize that when there is a net force acting on the ball, and that might be a combination of forces, but in this case, let's just say that our only force is the normal force that's on the ball by the broom. The direction of that vector, so I'm going to put an arrow over here, represent this is actually a vector, a force vector. The direction of that force vector is the same direction as the acceleration. So in order to cause an object to accelerate, you have to have a net force acting on it, and the direction of the acceleration will be the same as the direction of the net force. So I could add to each of these, and looks like I lost my pens. Here they are. That are different colors. Add to each of these an arrow that also represents the acceleration, and the acceleration will always be towards the center of the turn here. Now, this net force there's another word for the net force when we're talking about circular motion, and that is going to be a centripetal force. The symbol for centripetal force is going to be an F with a C subscript, where the C is just standing for centripetal. Now, centripetal force is actually the same thing as a net force. So the centripetal force is it's a combination of forces acting radially that cause an object to change direction. Now, this radial direction has to do with looking at a circle and considering that a circle has a radius, which can be drawn really any direction from the center of the circle, and all of these would represent the radius, which I'm representing with an R here. And so the radial direction doesn't necessarily have to mean that it's pointing outward from the center of the circle, but really anything that's acting along this direction that goes either from away from the center of the circle towards the center, or from the center of the circle towards the outside. So the radial direction just means any of these directions that are either towards the center or out from the center. So you might have the case where somebody is like spinning an object hanging from a string. So let's say somebody has like a yo-yo and they're making this circle with that yo-yo. If we look at this kind of straight on, we'd see that at the bottom of the yo-yo's motion, there are combinations of forces that are acting on that yo-yo. So if I look at the free body diagram, when the yo-yo is at the bottom of its circle, it's going to have a gravitational force pulling it downward because the yo-yo has mass. But then it also has to have this upward tension force that's on the yo-yo by the string that's pulling it up. And you'll notice that there is a winning force here. The tension force is greater than the gravitational force because overall there has to be an upward net force acting on this yo-yo. And the reason that you have to have an upward net force is because I'm trying to get this yo-yo to change its velocity from being directly towards the east here to actually moving upwards and less so towards the east. And so in order to change the direction, you have to think I have to push the velocity or push the yo-yo in a direction that's towards the center here to turn that vector from being sideways this way to actually tilting up. So the net force here is going to also just be called the centripetal force. So FC is going to be equal to, and I'm just going to define that up is positive and down is negative. So the tension minus the gravitational force. So here I feel like we should also define a term called centripetal acceleration. So as I talked about, this net force here causes the object to change its direction. We can also define that define a centripetal acceleration, which is a change in velocity. Just like always, acceleration is defined as a change in velocity. But here, centripetal means that the change in velocity is due to the object changing its direction. Now, all of this is really connected to Newton's first law, which states that an object in motion will continue in motion in that same direction unless it's acted on by an unbalanced force. So here we have an unbalanced force, like at the bottom of the yo-yo's motion here, the tension is greater than the gravitational, so we have a net force pointing up. And so that unbalanced force doesn't cause the yo-yo to speed up necessarily, but it does cause it to stop from moving in this direction that would be kind of continuing its motion this way, straight out. and instead it causes the object to change its direction. Now let's think a little bit about free body diagrams and circular motion. Now in general, free body diagrams, or FBDs, are really just the exact same as we've done them before. You're just going to identify the forces, and that might be gravitational force, tension force, a normal force, friction force, could be a magnetic force, and all the other types of forces that we've talked about. And so identify those forces and draw them as vectors on the object. And then consider the direction of acceleration. And make sure that there is a net force in that direction. So F net. So F net must be in the same direction as the acceleration. And in the case where the object is turning, that's going to be towards the center of the circle. So if you have something turning like this, then the net force and the acceleration have to be directly inwards at this point, and then kind of inwards here and inwards here. So it depends at what point of the turn are you talking about. Now let's do an example of a free body diagram involving somebody kind of spinning an object here off of a string, so maybe it's a yo-yo again or something, and they're doing it in a circle kind of like this. So I'm going to kind of draw this at a little bit zoomed in angle so we can see that the circle does something like this. So the center of the circle is right here. This is kind of an angled view. And the direction that the string is pulling this yo-yo at this point is directly along this string. So if I'm thinking about the free body diagram, the tension force has to be angled like this, Ft. And then you also have a gravitational force downwards. And so the question might be, well, where is that inward seeking force that causes the object to change its direction here? And the component forces that we learned in the forces unit still applies here. So if I break this diagonal force, the tension force, into its components, it's going to have an upward tension force, Fty, and that should be the same length as the gravitational force. So the yo-yo here doesn't actually, it's kind of making this circle parallel to the ground. It's not getting closer to the ground at any point. So it's not accelerating vertically. So that's shown by having these balanced forces in the vertical direction. But there is an unbalanced force horizontally, Ftx, that's pulling this object towards the center of the circle. So here we would say that, you know, the net forces acting vertically would be the vertical tension force minus the gravitational force, and ultimately that comes to 0 newtons because they're balanced. But then horizontally, the net forces in the x would be the Ftx, and really that is the centripetal force. There's no outward force here, so the centripetal force is a combination of center-seeking forces, so in this case we just have the horizontal tension force. Now I'm going to let you practice some other free body diagrams for different situations that involve changing direction. One of the ones that's really good to think about is when you're going over a hill. So that's going to come up in your worksheet, and give it your best shot, and then we will go over it by looking at the key tomorrow.
All right. Hi, everyone. Thanks for watching that. Sorry, I had some technical difficulties figuring out how to set up the camera to see everything. I won't be becoming a YouTube star anytime soon, but thanks for watching, and I'll try and get better as we go here. Okay, thanks. Bye.